Okay, so good afternoon all. But today we shall discuss about another very important and advanced topic, that is probabilistic method. The probabilistic method is very important to understand randomized algorithm. Okay, so at the and as in parallel first year ECB section, lab class is going on. So I can't take a double lecture, so I will restrict myself to provide a single lecture. And the second lecture means 4 p.m. to 4:50. That lecture we can schedule tonight at around 9:30 p.m. if the group is allowing to do that. Okay, so let's start. So probabilistic method, uh, it's a method which will lead us to understand randomized algorithms. So probabilistic method, okay, randomly chosen from or a set, or you can call it a space. Some probability. So consider where we have to determine solution. Solution say x. Okay. Probabilistic method, an object, an object, okay, is randomly chosen from a class or set or space with some probability. Okay, as probability is always lying in the range 0, 1, that is probability is always positive. Okay, you can surely have a solution, a feasible solution. So that means we are surely having some answer, feasible solution that will satisfy the given problem instance R. Okay. So this method pioneered by hello Hungarian mathematician called Argus, who is also the doctoral advisor of uh, Joseph already heard of Kruskal's algorithm. So Paulardus was the mathematical scientist who was also the doctoral advisor of Kruskal. Okay, so this method is combinatorics, theoretical computer science. So to very one to understand probabilistic method, let us illustrate with the help of an example. So one very popular example, okay, probabilistic method cut problem. Max cut problem. Okay, let's go for this max cut problem. So cut graph G equal to subgraphs such that space is partitioned into two subsets, vertices S and S bar. Okay, S bar equal to V minus S by a cut comma S bar. Okay, such that one edge belongs to the cut must have one endpoint and okay, mathematically we can write this. Okay, we will write later. One point is and the other end point or end vertex x edge u comma v belongs to Excuse me, what happened? Belongs to part S comma S bar comes to S comes to. Okay, so this is the definition of a cart. Okay, and we know that the size of cart is given by okay equal to s comma is, so this is nothing but the set of edges which belong to this cart. So the cardinality, that means the number of edges belonging to this cart, is the size of the cart. So cardinality of this set is equal to the number of edges. Okay, so our goal is to problem next cart problem is to determine maximum size of the cart. Problem hard problem, not NP complete but NP hard problem. Okay, now we see, to design an algorithm for this NP hard problem, we can design a randomized algorithm or a probabilistic method. Okay, so let's go for this. We have a theorem that okay, where cardinality of E is equal to n, number of edges equal to n, exists of which size is of which size is equal to okay. So this is the theorem, and let's proof of this theorem using probabilistic method. So the proof of this theorem will consist of three steps. So state, you know, formation of probabilistic. Okay. So here what we have to do, uh, select any RB, sorry, it's V, okay, uh, V, put it in space of vertices or a set of vertices A, or S, and into the space of R with some probability. Okay. So thus we shall random cut. Okay. This is S and this is S bar, and I may put this is, let's say, vertex, or this will be my vertex V. Okay, and I will have some probability to put that vertex V into S, or I will have some probability to put that vertex V into the vertex set S bar. Okay, next what we do in step 2, that is computation of expectation of uh, computation of expectation. Okay, what is that? Consider, okay, let's consider random variable as follows. Random variable corresponding to selecting a vertex V, selecting a vertex V, okay, V into space S or S bar as follows. Uh, X suffix E equal to 1 if okay. So I can put a vertex into S and another vertex into vertex set S bar. That means if I consider an edge, okay, like this, okay, if I consider the edge like this, let's say this is U, this is U. So if I consider an edge which belongs to this card, this is an edge belong to the card, edge card. One vertex is belonging to S, another vertex is belonging to V. So what we are trying to do, selecting a vertex into S and another vertex V into S bar is equivalent to, okay, selecting an edge like this. Okay, so we corresponding to selecting an edge into, okay, into card space, which is a forest. So XE is equal to so as follows: into random card space, which is follows: equal to 1 if E belongs to S bar, or it is equal to 0, otherwise. Okay. So then I can say that in consider another random variable x size of card S bar. Okay. So then we can write that is simply the number of edges belong to the card. So we randomly select a set of edges and check this whether that edge belongs to the card or not. So if that is an edge into a card, we simply put x equal to 1. Okay, so let's say we are taking randomly 10 edges with some probability. So 10 edges, so x1, x2, x3, dot 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 x10 we shall get, and out of 10 such edges, there may be 4 edges which belong to the card. Okay, that means the number of ones will be equal to 4, right? So now, so how to get that summation, right? If I compute this summation over xe, that will give us the number of edges belong to the card s comma s bar. So where a e is belong to, and we have cardinality of e equal to m. Okay, so this is your size, that is equal to cardinality of s comma s bar. Okay, but what will be the value of x? So what we are doing now in step 2, that is computing the expectation of this x. Okay, so in the next line, E bar is equal to, sorry, this is x bar, and this is equal to the expectation of x. Okay. Next line, expectation of, okay, the summation over x suffix where e belongs to that h set e is equal to n. Okay. Next line we shall have summation over uh, expectation of, summation comes out of the expectation. Uh, this is ordinarity of e is equal to, okay. So in the next line we are having expectation of e. Okay, this much we can write. Okay, this much we can, and let us give this result. Okay. This result 1. Okay, this is x bar. Okay, so now what we have, so now what will be the value of the expectation of xe? Now what is xe? Xe is a random variable which represents that an age belongs to s comma s bar. The question is, how can an age belong to the cart s comma s bar? Okay, so considering u comma v, which can, which s bar in two ways. One is one is u belongs to s and v belongs to s bar. Another is u belongs to s. So there are two ways in which the age u comma v belong to s comma s bar, right? So hence hence the probability that age u comma v belongs to comma s bar okay. So if this probability is half, immediately we can infer that the expectation that implies expectation of XE. So from 1 we can write that we can have the following, that is R summation over half for all edges belong to H set E, where size of E is equal to M. Okay, so it's a summation on a constant value. Okay, so in the next line we shall have half into half comes out of the summation, so 1 plus 1 plus dot 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 up to M number of terms, that is M, so M by 2. So expectation of this is equal to M by 2. Okay, and this is the minimum number of expectation, which gives us the minimum number of minimum number of size of the cart. Okay, so which is the lower bound we are getting in this case. Okay, so this is bound, hence we can say that cardinality of S comma S bar is greater than equal to M by 2. It is not less than M by 2. Okay, so we have proved that. Final conclusion, that is, for any graph equal to V comma E, there exists a cart S comma S bar of size greater than equal to, clearly it's an NP-hard problem. We are not able to find a deterministic algorithm for this. Okay, and also it's an optimization problem, and it's not possible to construct this, solve this problem in a polynomial time. So it's an NP-hard problem. Okay, so so it's 4:03. We have to stop here. If you have any question, you can still ask me. So next class, we resume our topic either on randomized algorithm or an approximation algorithm. Okay.